Welcome to PavementDesigner.org. In this short video, I will show you a step-by-step walkthrough of a jointed plane concrete pavement thickness design. So we begin by starting a design. Once we've started our design, we have to select a project type. Jointed plane concrete pavement designs are typically in our streets and local roads. So we can begin here. To do a jointed plane concrete pavement design, we have to select full depth concrete. Once we've selected our concrete pavement, then we need to input our project level details. As with the other methodologies within PavementDesigner.org, all of our design methodologies are broken out into project level details, pavement structure details, and our summary solution. You'll not be able to advance to the next step of the design without inputting all of the details within the step that you are currently on. So first we will select our project level details. Here we need to define our traffic and our global inputs. The first step is defining our distribution of our traffic. Our distribution of our traffic is broken down into a traffic spectrum. Here we have 8 default traffic spectrums: a residential street, a collector, a minor and major arterial, as well as ACI 330 traffic spectrums A through D. If you have good details on your traffic, you can also input a custom traffic spectrum. Here you will need the axle load, an axle load, as well as the number of axles per 1,000 trucks within that spectrum. For this example, I'm simply going to select a minor arterial. Additionally, if anywhere along your design process you have a question about the design input, you can see that there is guidance or help screens with every single input. Here you can see our details on selecting a traffic spectrum. For more information, you can select more information and see some of the details that are housed directly on the site for a given input. You can also turn these help screens off if they're disruptive in your design process. Our next input is our design life. For this design example, I'm going to select 30 years. Our next step is to give some more details on our traffic inputs. Here if we're directly inputting our user-defined traffic info, we can put our trucks per day, define our traffic growth rate in % per year if we expect our truck traffic to grow over time, and then we can distribute our truck traffic in a direction if we have our truck counts in each direction, and we can also distribute it over a number of lanes if we have multiple lanes in each direction. You can also define your traffic based on existing asphalt design. To define your traffic based on an existing asphalt design, we need to input an existing asphalt design. Here we can select our number of layers within our asphalt design, as well as the materials, and then the details on each of those individual layers. We also can select our reliability as well as our subgrade resilient modulus and some other design parameters that are required to get the full asphalt pavement design. Now this module is actually based on the AASHTO 1993 design guide, and from this, Pavement Designer will calculate the structural number of the section as well as the allowable flexible easels of the section. And then, using the traffic spectrum defined here, the average trucks per day and the total trucks per day or total trucks over design life can be estimated for our concrete pavement design. For this example, I'm simply going to directly input my user traffic data. So number of trucks per day, I'm going to select 500. My traffic growth rate I'm going to select as 1%. I'm going to assume that 500 trucks per day is distributed over 2 directions, and that 90% is going to be in my design lane, with 10% being in the passing lane adjacent to it. For reliability, since this is a minor arterial, I'm going to select 80%, and I'm going to expect about 20% of my slabs are going to be cracked at the end of that 30-year design life. Once all of these design inputs have been provided, our calculated traffic results will be automatically calculated. You can see that our average trucks per day in the design lane over the design life is automatically calculated as 261, and the total trucks in the design lane over the design life is also calculated. These calculations, again, are based on the 500 trucks per day that we have total over the total in the facility, distributed over 50% on the, say, northbound direction and 50% on the southbound direction, and 90% are in the driving lane, with 10% being in the passing lane. Thus, my driving lane is my critical lane and my design lane, and that is where this 261 comes into play. Once all those design details are input, we can move on to our pavement structure. Once we select our pavement structure, this is where we can design for jointed plain concrete pavement, or JPCP, or roller compacted concrete, or continuously reinforced concrete pavement. For this design example, we're designing a jointed plain concrete pavement. If we decide later to select one of those other options, we can simply select here and change our pavement type. So now we need to define our pavement structure details. And this includes our details on our subgrade, our surface concrete, as well as our structural layers, or our sandwich layers in between our subgrade and our jointed plain concrete pavement surface. Our subgrade can be defined by the resilient modulus of the subgrade, or we can convert from a California bearing ratio, or CBR, or a resistance value. These built-in conversions are a simple conversion that will get us a modulus or resilient modulus of our subgrade. Next, we need details on our surface concrete. This is typically defined based on our concrete strength. Flexural strength is the design property needed for our concrete, but it can be calculated or estimated from a compressive strength, the modulus of elasticity, or the split tensile strength of the concrete. In this example, I'm going to assume that I have a compressive strength, and that the compressive strength is around 4,000 psi. Our calculated flexural strength converts to about 580 psi. Next, we need a modulus of elasticity. This value is defaulted to 4 million psi, but can be changed within reason. We can now select whether or not we have macrofibers within our concrete. This is defaulted to no, but if we do select yes, then we need our residual strength of those macrofibers. For this example, I'm going to assume that we don't have macrofibers within our concrete. We can also select whether or not we have edge support. Edge support can come in a variety of different forms. The first being a widened lane on our drive lane, or whether or not we have a tied concrete shoulder. If we simply have an asphalt shoulder, we would assume that we don't have edge support. For this example, I'm going to assume that I have a tied concrete shoulder. Next, we need to define our structure layers. Our structure layers can be anywhere from 0 to 3 layers. For this example, I will assume that we have one structure or subbase layer. Next, we need to define what type of layer it is, whether it be a cement treated or asphalt treated base, or whether it's a simple granular base. Each of those layer types has a default resilient modulus that can be altered. Now we need to provide a layer thickness for each of the subbase layers. For this example, I'm going to assume that I have 4 inches of a granular base at 25,000 psi in between my subgrade and my concrete pavement surface. Once I've input these details on my subbase, as well as my subgrade layers, a calculated composite K value of the substructure is provided. This calculated value can also be overridden by the user. If I assume that my structure is actually weaker, I can put in a different user-defined composite K value of the substructure. For this example, I'll just assume that I have a 200 psi per inch K value underneath my concrete pavement. Once all of our details are provided for the pavement structure, we can move on to our design summary. Here we can see our calculated minimum thickness of our concrete, our recommended design thickness, as well as a maximum joint spacing recommended for our jointed plain concrete pavement. You'll notice that the minimum thickness is the minimum thickness required to carry the total load for that entire design life, the 30 years that we defined back in our project level details. The recommended design thickness is rounded up to the nearest 1/4 inch. You'll notice in this example that our dowel's recommended design thickness is grayed out. That is because we typically do not recommend dowels being placed within any concrete pavement that's thinner than 7 inches. This can provide some construction issues. It can be done, but it's not typically recommended. Additionally, you can see that we have some sensitivity plots within our analysis section. These sensitivity plots can show us the change in thickness based on a change in a design property. You can see that if we change our K value over time, if we increase the structural strength of our subbase and subgrade layers, you can see that it has an impact on the surface level thickness of our jointed plain concrete pavement. Similarly, if we increase the concrete strength, it will also have an effect on our concrete thickness as well. If we change our design life and assume that there are more trucks that the concrete pavement is going to need to provide structure for, we will need additional thickness as well. If we change reliability and assume either we want our design to be more reliable or less reliable, it will also have an impact on our concrete thickness. And if we alter the percent slabs cracked, if we want to assume that 5% slabs cracked at the end of our design life, it will also have an impact on our concrete pavement thickness. We can also view within the analysis section cracking and erosion reports. These reports show you the level of fatigue or erosion that's consumed over the pavement's design life based on the traffic levels that we initially input back in our project level inputs. You can see here that we consumed 98.85% of our concrete's fatigue life. That means that we're assuming that our concrete pavement design is failing by cracking at the end of our pavement's design life. If we look at our erosion consumed over the design life, we can see that only 6% is consumed. 6% of our erosion life is consumed over that 30-year design life. So once we've evaluated whether or not this pavement design is the pavement design that we want to follow, we can generate a report. Here we can input additional details on the concrete pavement design. For this, for demonstration, I'm just going to input some default values. Route 1. And then we can generate our report. The report is automatically provided and features all of those inputs and all those details that I just provided within my design. You can see that all of the design summary and all of the design inputs are also featured within this pavement design report. This report can be printed or downloaded automatically straight from the web. If we decide that we want to save this design and come back to it later, we can save it assuming that we are logged into an account. We can also create folders to house these individual projects if we're doing multiple designs for a project. We can then access that design later in My Designs. We can then either edit the design, copy it and alter the design, or we can share it with someone else. We can also delete the project if we decide that that's not a project that we want. So this has been an example of a jointed plane concrete pavement design using PavementDesigner.org. For details on any other type of project, you can find those in the resources section. You can also contact a local expert on concrete pavement design if you have questions about doing a pavement design with PavementDesigner.org. Thanks.